All right, Hoon School, I guess HSL 3, since we're numbering from 0. So welcome back. We delved into tree structures and lists and started to get into cores and what's going on with those, which will prove to be a very important concept a little bit later today, but in particular, next week, we're going to get very, very deep into cores. What Jack and I wanted to do today is circle back around and take a look at text in Hoon. Like, how do we actually represent messages? So ultimately, everything on a computer is a number, right? It's a value in zeros and ones and bits that are on your machine in whatever representation, and your computer has a way of interpreting what's going on as an instruction or a value or an address. And so there's some sort of interpretive rule that gets put on these values that allows us to treat these raw numbers in the machine as text, ultimately. Now, of course, the files that we've been writing in Hoon are text, but these are generally getting treated as code, right? Like they're not getting pulled in and processed as text, as a message. They're getting treated as structural information about the way the program is working. But whenever we want to display a message to a user, when we want to store a Hoon source code file or other data, prior to interpreting it as code, prior to building whatever structure and memory that is yielded by it, we have to think about what's going on with the text. Now, many programming languages, probably all programming languages, I mean, I say many, but everyone has to deal with text at some point, right? Like the ability to actually represent messages as distinct from code or comments or other things that are directed at the machine or the programmer. Now, one of the reasons that we don't just call it a string in Hoon is because there's actually 4 basic ways to represent text that we use for different purposes here. 2 of these accord pretty closely to what we would call strings and other programming languages, that they're single characters in memory sequentially. So it's not as simple as just having a character array. There's more going on whenever we start representing and working with text. And they have different facilities. They're useful for different things. Some of them are easier to process. Some of them are easier to store or transmit. So we will be switching back and forth between these things. So in the, I guess, let me give you, I do this sometimes where I'm like, I need a little bit of a philosophical background to make to start this off. I'm not going to go real deep, but I want to talk a little bit about where these messages come from. And I think I lost my Zoom. No, it's not. No, it's not letting me share. A moment here. Okay, you should see the semaphore, or most of it whenever Zoom gets out of the way here. All right, so when we think about what a written character is, there's some kind of representation of human meaning to this symbol, right? An alphabet prescribes a particular relationship of a sound to a symbol. Of course, you can do syllabaries, you can do ideographic and logographic scripts, you can do other things. Here there's an example of semaphore. And so we talk about storing characters. Sometimes we'll say letters, but character is kind of a broader way of talking about this idea of transmitting the concept. So back to what I was talking about earlier with respect to the computer. Some of you will have run across ASCII before if you've done much programming. If you have not done much programming previously, then you may be dimly aware of this or not. But The idea of ASCII is that it's a standard code that maps a number, the value that's actually in your memory, to its interpretation as a letter. And so here we have columns of decimal, hexadecimal, octal, which is almost never used, and HTML codes for each of these values here. So if you want to write a message like hello, what's actually stored on your computer is a 72, a 101, a 108, a 108, and a 111. And somewhere between that place in memory and the display that you see on your screen, there's an interpretation that takes place that says, we're going to treat this particular sequence of numbers as if it were letters. And so this is what we mean by a text string. It's a string of numbers in memory that are sequential to each other. Now, there's a lot of other characters here. So, obviously we don't have Chinese, we don't have Japanese, we don't have diacritic marks on these. So there's a much broader scheme than ASCII called Unicode that assigns a number, a unique number to essentially every character that a human has devised as a way of writing down this kind of semantic content. There's an Egyptian block, there's a Cherokee block, there's all sorts of things in there. Not literally everything, but there's cuneiform, there's Sumerian cuneiform, but there's not Hittite cuneiform. So there's some gaps that I'll be worked on later. There's a whole proposal to put in Mayan glyphs. And so that greatly extends our ability to write values beyond just these regular characters. However, the symbols from 32 to basically 126, because we're not explicitly including the delete character or the control characters at the beginning for the most part, those symbols are the things that essentially make up code in basically any programming language. This is the common set that's available to any system that you are working on. Now, all right, let's go ahead and back to here. All right, so when we start dealing with things in Hoon on the machine, we're going to be able to basically look at this representation directly and see how it's behaving. So let me go ahead and start a Urbit. Let me share another screen with you. We'll jump over to Urbit and look at what's going on with the text representation.
What does the Bible say? The Bible says waters below the firmament, waters under the firmament, waters under the ground.
Not immediately clear to me why that's a relevant argument. All right, there we go. And all right. And Urbit, Zod, start your Urbit. And here we go. Okay. So if I assign a code value to every character, if I wanted to write a message, then I should be able to take those letters that I was talking about a moment ago and use them as some kind of representation here. So we are going to start with, I'm actually going to start with tapes, which is one kind of code, which is a message here where so if I were to write the ASCII characters in order here, all right, so does this look like a string? One of the tricky things about strings is that this is what Urbit would recognize, what Hoon would generally recognize as a null terminated tuple. It is shaped like a list, but it is not a list until we explicitly tell Hoon that it is a list. This is something that still occasionally trips me up when I start working with this. So we're going to call this a list of characters. Why aren't you happy with this? Oh, because you want me to turn it into a list of atoms first. sometimes you have to do this where you have to turn it into the more general type first, and then you can turn it into the less general type. All right, so then you can see there I have a list of single characters, which are ASCII. So 65, 83, 67, 73, 73 in order. Let me see directly what those values are. Let's see if Urbit will let me simplify this statement to a tape. Nope, see what's happening is if I haven't explicitly marked it, in general, if you get what's called a mint nice error, this is it's a nesting error. It's saying that one thing doesn't fit inside of another. So in this case, it's saying a tape is a list of characters, which, from what we saw of lists last time, this should be moderately intuitive. It's just characters in sequence that are terminated with a null character at the end, but we haven't told it it's a list, and so that's why I have to do this. I can tell it I want a tape. I can tell it first to generate a list of raw atoms, and then I can do my 65, 83, 67, 73, 73. All right, so in that character, okay, so in that case, it all came out nicely, and this is what we got written with double quotes here. Anytime you see values written in double quotes, it's a tape. It's a list of those characters in sequence. So they're just slotting into memory. The way that we were thinking about binary trees last time would work here as well. So if I were to refer to the 2th address inside of ASCII, what character would I get out of that? Think about that from your tree-based stuff for a second, and give me an answer there.
A.
Let's test it. Yep. All right, Jack, it doesn't hurt for them to see it 15 times. We're going to do a lot with trees. And so we should be, so we should be able to jump up and pull all of those. So those will all be in order. So this is your basic text idea. Now, there's another kind of text which we commonly use, which is to write it in single quotes. This is what's called a chord. So let me take notes here for you. So a tape is a list of characters. A chord is just characters sequentially in memory. And the difference is, if you think back to what a noun is either an atom or a cell, where a cell is a pair of two nouns. Here, what this implies is that a tape is a series of cells. A chord is an atom. So a tape contains individual characters, but a chord just stores all of them sequentially in memory. So if I were to take this same character that I had a moment ago, that's ugly. Let me turn it into a pat UX, and then take this one that I had here and turn it into a list of pat UX. Oh, come on. So finicky about lists. All right, there we go. So compare these two answers that I got here. What do you notice about the order of the characters in memory? What do we see about the relative order of these characters in memory? So the list, the tape, moves basically from left to right. These are the hexadecimal equivalents of these decimal numbers. So we get the 41, the 53, the 43, and so forth. What's happening here? Pairwise, they're all present, but they're in opposite order. So it turns out that this is what we call a least significant byte first atom. This is the general order of atoms. It means that the last character in text is the leftmost character in the numeric representation that we have here. Then there's a couple of other ways of writing characters, knots and terms that we'll run into as well. So a knot, well, actually, let's look at all these close to each other. All right. So what kind of thing is this? Yeah, Daniel Vortex asked if this is little or big endian. I can't remember which is which, but yeah, this is basically where that decision is made. Where we're doing least significant byte. I guess little big endian would have more to do with like the way that the machine is representing it at the CPU level, if I recall correctly. I guess maybe we'd call this little endian if we were going down that road. Anyway, all right. So what type of thing is this in single quotes? Hello. What mold does it match? No one gonna bite? How do we find out? Do you remember how we figure out what kind of mold something has? It is a chord. If you're not sure, we introduced in the notes, at least, I think we talked about it in the lesson, but but in the notes, you can also use what's called the type sphere. It's the head. Zapgar generates a pair of type and then the numeric value of whatever the thing is that you're looking at. So it's the type and the value. We call this a vase. So if you take the head, the left-hand side of this cell, you get just the type. So we call this the type sphere when we do it this way. So if you're not sure, that's what you can do. You can pull this information out and you can see it. All right, so if I do that with hello, it tells me it's double quotes here, but that's the way that it represents a tape. So right now we have two kinds that we know about. If I were to take the pat T chord and run it as a pat TA, it drops a sig dot in front. The content doesn't actually change, but this is like an ASCII. It's a limited set of characters used for like things like file paths. Like we want to talk about a file or a URL. You can't use literally any character in those, right? Because certain characters have special meaning. So you can't, if you're on a Windows file system, you cannot name a file with a backslash in the name of the file. And there are other characters that are limited in this regard as well. Even spaces can kind of give you some trouble if you're actually trying to work at the command line with them. And so the not is a limited set of characters. We prefix it with a sig dot here so that we know that we're uniquely dealing with a not, with a pat TA. We haven't lost any information. So if I were to do sig dot hello, and if I were to convert that to a pat UX, this would have the same content as the chord version of it. It's just a different type, a different interpretive rule that we are attaching. So we can indicate to Hoon in the way that we are writing things, the kind of value that they carry. Then there's one more of these, which we're going to call a term, which is a pat TAS. We use these as text constants or identifiers inside of Hoon itself. They are general text, but they will show up with a % sign in front. And so if I were to write pat UX of send hello, I would still get the same value. In every case, I get the same result there. It just shows up a little bit differently when it prints for me. Now, one of the things, you might say at this point, okay, so like, great, why bother? Why does this matter to us so much that we have all of these? So tape and chord matter the most. You're going to use them most of the time. because tape is a list, it's a little bit more wasteful of memory, and a chord is a little bit more compact. So generally speaking, people are going to store data as chords, and they're going to process data as tapes, and we can convert back and forth between them. So there's different operations we can do that will let us work on text next to each other. So if I have a string like hello as a chord, if I run trip on it, I can turn it into a tape. So trip is my chord to tape conversion function. Tape rip is the acronym though. The other one is chord rip, which accepts a tape and converts it back to a chord for me. Then there are all of the list operations that you're going to start using and getting comfortable with. Because a tape is a list of characters, this means that you are able to use list operations directly on text. This is one of the reasons we like using these for text. It's an easy way of, we can find things inside of it. So let me see. So if I'm going to find, let's find the letter E in Hello Mars. All right, so it returns to me a pair of things, and this pair is a null value and a 1. So what it's telling me is that at the 1th position, it found the E. So it starts counting from 0. Generally speaking, Hoon counts from 0. So this would be 0, 1, 2, 3, 4, 5, and so forth. If we look for a character that's not present, like P, then it'll return to it. So this is it's a value called a unit. We're going to see more of this later on, probably about lesson 6. We'll start working with these seriously, but it lets us distinguish between, we found the character at the beginning, which is at 0, of course, and we didn't find the character at all. So we're gonna use that to make that distinction there. There's a lot of other text operations that we can use. Somewhat humorously, if we cuss a word, it uppercases it, and so forth. We'll have all these in the notes, but these are basically the kinds of analysis that we can do as we start working through and processing text. So that's the capability that we're going to be introducing and testing you with in this lesson before we start working on deeper code. So we're elaborating. Here's the way that you can start working with the data, because data are generally stored as text in some form, and start processing those and get used to that idea. Now, let's see, it is 8:54. Before I talk about, let's see, Jack, were you going to get conversions like Scott, or or was that on my docket?
I think that's yours.
Okay, I'll talk about those in a moment then. So let me see. Let me list some of the things we saw here. So crip, tape to chord. Trip is chord to tape. Find. Really locate one list in another, but one string in another, right? Because a tape is a value there. What does weld do? You may have run into weld already in the homework. If not, then we're introducing it now. What does weld do for me?
Appends the list.
Sorry?
Appends the list.
Yeah, so it glues them together. So we'll do that with 2 lists. Let's see. I think those are the only cuss, uppercase. There's a cas, which is the opposite, which is lowercase. Some of these are good mnemonics in that they're easy to remember. Like weld is easy to remember. Cuss it's a little bit of a pun, but it's easy to remember. Find is easy to remember. Cas is a little bit harder. There's probably a mnemonic for it if you could think of it, but it's not like immediately obvious to me. Chord rip and tape rip are more obvious if you know the root of the mnemonic for them. There's a ton of other list operations. We're going to link those for you. You'll get an idea of how to look at those. Now, one of the things that you most often want to do, let's say we have a value like 2 as text. If I were to convert this number to a pat UD, I get the number 50 out. So if I want to convert text like the number 200 to a Hoon value of 200, I can't do it by just treating the text as text. If you haven't run into this before, this may be a little bit surprising, but essentially what this is that the 2 is literally stored as whatever the character code for 2 is, which is decimal 50 and hexadecimal 42, or something like that. What the, I guess 32. 200 is actually stored as the characters in text 200. And so if I were to look at the pat UX version, I'd see here's my 2, which is hexadecimal 32, hexadecimal 30, hexadecimal 30, 200. It doesn't correspond to our idea of value, that we actually want the number 200. So commonly, you're going to read data from a web source, from a file, from user input, user typing, and you have to get it from that text value to an internal number because you're going to do some kind of processing on it. Or you've asked someone, what's your urbit ship? Type your urbit ship for me. Well, if I try to do, a pat p of, the pat p is the urbit type. If I do it of like sig zod, that works. If I do it of sig text zod, it does in fact convert it to a pat p for me, but it is not the correct pat p for the same reason that this is literally the characters in memory sig zod. There's nothing else there. We're going to use Scott and slaw to do these kinds of conversions. I don't think we worry too much about slaw this time. So what Scott is going to do is we're going to give it the name of the kind of thing we want. And we're going to give it the Hoon value. And so this is Hoon to text. Actually, it goes to a not, but you can treat it as a chord because those are directly convertible with each other. So we can do, so if we want to do the conversion one way, we can do that. If we want to do the conversion back, there's another one called slaw that will go the other way. It'll pull the value out of text and bring it back to us. All right, so both of these, what they're going to take is a symbol of the value. You notice that we're doing with this with a send p because we want the name of the type. We don't want pat p itself, which is, pat p is a gate, it's a mold, it's a type. And we don't want the type, we want the name of the type. It's sort of like in mathematics, sometimes you want to talk about the value of a sign function, and sometimes you want to talk about the sign function itself, like, the way it behaves. And sometimes you want to talk about the name sign function. Those are 3 different modalities of interacting with it. So here what we're going to do is we're going to choose the name. So like this one wouldn't work because I can't convert that to a Hoon name, but I can convert it to a unit of the Hoon name, or excuse me, sig, and then the null, and then the value that corresponds to it. So I know that 0 is zod is the root. So I've done that conversion successfully. So Scott and slaw are going to let us do text conversions forward and backward as we put these things together. So this is what we're going to be doing whenever we need to pull in text and work with text. So there's a lot of ways to process, to convert. There's a whole battery of things that do very sophisticated conversions. You'll notice that when I wrote the text here with slaw, I had to write the text as the German style thousand separator, like it had to be valid Hoon. If I were to do the same thing with 54,321, it would fail. It gives me null back. It failed to carry out this conversion. There are other text converters that are more flexible that we will introduce later on. Right now, we're going to stick to, do we have pure Hoon expressions ready to hand? That's where we're starting for right now. Any questions about text operations before I hand this over to Jack? All right. That's fine. This is a great lesson for you to be following along with, by the way, if you're not, just because we're doing a lot, we're not writing long programs for the most part, we're doing short demos of what's going on. Anyway. All right. Jack, I'm gonna make you host as soon as yeah, there we go. There you are.
Hey everyone, can you see my screen? Good? Okay. And you can't see the floating portraits of everyone, right? Okay.
Right.
All right, so let's talk about lists. So we're gonna do a deep dive into lists, how they work, and why you want to use them, how you want to work with them. They're a super important data structure when you're working in Hoon. So yeah, this will be good to know. So basically, if you'll recall from lecture 1, a list is an ordered arrangement of elements which ends with a sig. And if you look at this graphic right here, that's how it's going to be stored in Urbit's abstract data tree. So this is going to be a list of 1, 2, 3. If you have that equivalent thing in Hoon, it's going to look like this. So here are 4 different Hoon expressions, which all are going to mean the same thing. Here, the first one, you can see it with the colheps, like in the tree. Then you can also compress the colheps to just the cell notation, and then you can compress the cell notation further. And the interesting thing about working with having lists be stored like this is they have a recursive nature to them. So in particular, if I take this list, I get rid of this 1, and I just look at the tail of the list, that is also a valid list by itself. So we just have a list of 2 and 3, and in the Hoon code, it's going to look like any of these equivalent representations. And something else that we introduced in this lesson that will be good to know is that here are 2 different ways of writing the same thing. So either you can put the sig as your last element in your list, or you can just put it out front like so. That's just like a neat little bit of shorthand. It's useful sometimes. All right, any questions on that part so far? If no, then I'll keep moving along. So formally, the term list in Hoon is what we call a mold generator. So it's a gate which takes as input a mold, including an aura, and it returns a mold. So this is how we would use that. So if you recall the senhep notation, that's just how we call gates in a lot of other scenarios, right? So here we're calling the gate list on PatUD, and most often you'll see it in this bottom syntax, which is just the short version. And what we're doing here is we're giving PatUD to list and constructing a mold of a list-shaped object with PatUD in every entry. Does that make sense to everyone? All right, cool. Sounds good. Good to see the yeses. All right, so if there's no questions, then I'll move on. All right, so once you have this list of PatUD like so, then a common way you'll use it is say you have a gate and you want to specify what kind of input the gate is going to get, then you can use it like this, specify you're getting a list pat UD, and you can use it with a fence to specify that this gate is returning a list pat UD. So that's kind of what the beginning of the gate that takes and returns a list pat UD might look like. So lists usually have the same type of thing in each entry. So this first one is a list pat p zod neck bud. The second thing here is a list of hexadecimal numbers, and this third thing here is kind of interesting. It's a list of list pat UDs. So every entry in the list is itself a list of pat UDs, and that's totally valid because if you recall, list takes any sort of mold as input. So you can do stuff like this. You can do a list of sets. You can do a list of maps. You can do a list of any data structure that you can create. But lists don't even have to have the same entry in each entry, or the same type in each entry. So here's just a list of atoms. So you have a text, you have a chord, you have a TAS, and you have a integer. And if you just parse them as atoms, they get turned to numbers like this, but it's totally fine that they're different types. So here's something that Neil mentioned earlier. So even if something like has the right structure of a list, so you have like several things that are the same type, and then you have a sig at the end, Hoon doesn't necessarily recognize that that's a list. You have to like explicitly force it to say this is a list. So if you look at the first example here, we have a list looking thing that says 3, 4, 5 and a sig, right? But we're going to use this type sphere right here. That's what it's called, the type sphere, to grab the type of this. And the pretty printer is telling us, oh, I think this is a 4 tuple of a pat UD, pat UD, pat UD, and a sig. So that's what the pretty printer thinks this is. But in this bottom example, if we cast this explicitly to a list pat UD, then the pretty printer is going to say, it's going to recognize that this is a list. And this syntax right here, this IT means an iterator. So that's just saying it recognizes this is a pattern on a pat UD, which continues indefinitely. So this, in short, this is saying it recognizes the list. Are there any questions on any of that? All right, if there's no questions, then I'll keep moving on. So recall what we said. A question. Is it best practice to always explicitly type the lists? Yes. In general, if you're using a list, you should just say this is a list, so and so. Maybe Neil has something to say on this.
So you actually have some interesting options here. One is, since a list is a mold builder, right? So if you use list, so list by itself is a gate that produces a mold. So it's a gate building gate. If you want to step back a moment and think about what that means. We're going to use this pattern a lot in Hoon. This is the first time we run into it is with list, but we're going to use this pattern a lot where we need a gate that does something specific for specific types and values. So we're going to use another gate to build it. So if you explicitly mark the type here, it means that Hoon is carrying around that this is a list, and the kind of list that is attached to it is, it's attached to pat UD values, and things that are not pat UD values cannot be welded to it. They cannot interact with it. So if you had a list of pat UX and a list of pat UD and you tried to weld them, it would fail because they're from two different worlds. But you could also do, parenthetically, you could do tick, pal, list, par, tick. Jack, do you want to try typing that really quick since you have a fake sod pulled up?
So what was that again?
Tick pal list par tick, and then just some list, some null terminated tuple, sig cell 1 2 3, something like that. Yep. And so if you give list no type argument, it uses the bunt type, which is going to be pat, so it will still fit everything. But we're actually invoking the function with no arguments there, is one way to do it. Which is kind of a roundabout way to say you have an enormous amount of flexibility in producing lists, but in Hoon, it is generally a best practice to mark your type explicitly frequently. Don't let it guess what it thinks you have. Tell it what it should have. And this will save you so much headache when you're debugging later on. It turns out that getting a Hoon program to correctly compile, like a non-trivial Hoon program to correctly compile, often means you're like 80% of the way to a debugged program. The typing system is very cantankerous, and if you can make the typing system happy by doing things like marking lists and atoms and so forth, use cat heps everywhere. If you can make it happy, then it will reward you by solving a lot of categories of bugs that you would run into in other languages like Python that don't have strong typing.
So Neil, there's a super quick question in the chat, because I gotta make time, but somebody asked, is sig a null pointer?
It's not a null pointer. It is a null value. Hoon doesn't have a notion of pointers. So I wouldn't call it a null pointer, but it is a sig. Like it's a null, it's zero, it's nothing. And in Hoon, those are all the same things. Null pointer being kind of a C-like operation, but Hoon doesn't know about memory. Hoon only knows about nouns. It only knows about trees. The memory representation of these things is a problem for the runtime. Whatever runtime is virtual machine is running the knock.
All right, so I'm gonna keep moving on with the list lesson. So if we'll recall, back here we said if you have a list, there's kind of recursive nature to it, right? So you can take the head off, grab the tail, and then that's also a list, right? And the special thing is, in Hoon, you can actually manipulate lists like this, and you'll find this very useful. But the secret is, and you have to remember this because like everyone gets tripped up on this, you can only grab the head and tail of a list when Hoon knows that the list is non-null. So the code here, we have my list, which we're declaring to be a list of 1 2 3. And then this what sig is saying if my list is null, then zap zap just crash. So that means when we're in this branch of the code, who knows that definitely my list is not null. So you have to do that even though you declared it up here and you kind of know what you declared it to be. But by doing this, who knows that when you're in this branch, my list is not null. And then you can get i.mylist and grab this one, which is the head of this list. And here it's the same thing, except now we're getting t.mylist. So t is how you grab the tail. And then we're getting as a result this 2 3, which is the tail of this list, right? And here, this is what's going to happen if you don't do that non-null check. So if we just declare my list and then we just grab i.mylist, then it's gonna complain because it just doesn't know, like it doesn't want to use the int unless it knows it's not null. So that's just kind of a small thing, but you guys will probably work with this sort of pattern using the int in your homework. So this is good to remember. Is there any questions on this?
It makes sense if you think about it, why it's picky about this, but sometimes like satisfying the type checker is a bit of a pain.
All right, so if there's no questions, I'll keep moving on. So what's the reason for using and storing data in lists, right? We have cells, we have tuples, but what's special about lists? The useful thing is when we know something's shaped like a list, that enables to manipulate it much more easily. And in fact, Hoon has a very rich standard library of functions which can do all sorts of things on lists. And getting familiar with these will definitely help you write better Hoon code. So I can't show all of them to you, but I'll just give you some examples. So here we have the list function flop. And it's pretty simple. It's just going to reverse the order of this list, right? Here's another one, snag. It takes as input index and a list, and it's going to get you the thing at that index, right? And can anyone tell me what's going on in the second example of snag?
Grabbing the one element from the tape of hello.
Yep, exactly. So if you'll just recall from the part that Neil taught, tapes are lists. So you can also just use list functions on them like this. And so another list function that's useful is weld. So we already covered this, but yeah, you're just combining two lists together. So here's just some examples of that, basically. And there's some more complex kind of, there's some cool list functions that are not just like these basic operations. So learning these will really upgrade your Hoon code. So one example of one of those functions is turn. So turn takes as input a list and a gate, and then it applies that gate to every element of that list. So here we have 2, 3, 4, 5 and dec, and then it's just going to decrement everything in that list. So that's super useful. And here's another cool one. It's called roll. Can anyone tell me what roll is doing based on these two examples?
Applies the gate to each member of the list.
Well, that's turn, right? That's because turn was we're applying this dec to each element and we're getting back another list, right? But here we're actually getting back, we're not getting back another list, we're getting back one thing, right? So here we're doing add and here we're doing multiply. So yeah, it's aggregating something, right? So
It's either adding or multiplying all the numbers together.
yeah.
Pair by pair.
Yep. So what roll is going to do is, so first it's going to add 1 and 2, and then it's going to take that 3 and it's going to store it. And then it's going to add that 3 with this 3, and then it'll get a 6 and it'll store it. And it'll add that 6 with this 4, and then it'll get a 10 and it'll store it. And then it'll add 10 and 5, and then you'll get 15 at the end. So that's like, this is a super useful pattern. If you learn to like use these functions, it'll definitely upgrade your code. And yeah, so this is the same thing except with multiply. So it's just multiplying 1 by 2 and then taking that 3 and multiplying it by 3, etc. So yeah, there's a lot more useful list operations. As I said, we can't go over all of them, but I'll drop a link in the chat so you can see where they all are in the docs. Are there any final questions on list libraries or lists in general? Yeah, you can define a custom gate. Yep, exactly.
A very common pattern is actually to write the gate in line right there where you need it,
Yep.
and then
Mhm.
apply it to the list.
Yeah, just write like a little gate right here. Mhm. Any other questions? All right, so the next part of the lesson is going to be about libraries. So a library is going to be a file which contains some standard utilities, like maybe some gates, a core, whatever that you might want to use in other parts of your code. So you can import the library and use the functions contained within. So if you've coded in other languages, this is a pretty common pattern, right? So let's go through an example of a library. Here's some code. And let's save this as, let's go to our urbit, go to our base lib, the lib folder, and save it as tapes.hoon. So what is going on here? So we have, let me make this bigger. So what's going on here? So we have two arms in this bar send core. This first arm is called break. It takes as input a tape and it returns a list of tapes. And we don't have to go through this whole block of code here, but basically what it does is it takes an input tape like a sentence and it's going to return you all the words in that sentence broken up. And this one called count, what does this do is it takes as input a list of words and also a word, and then it's going to count how many matches to that word were in that list of words. So this is just to like, this is like a common pattern. So you'll have some like commonly used functions, you'll put them in the library and then you'll call them somewhere else, right? So if I want to call these from the dojo, I can actually do that. So I save these to my lib folder, and then I go back to my Zod and I commit. And then see that showed up. And the way I call them is first I need to build the file. So I'll call my file tapeslib, and I'll use this build file thread, and then I'll give the thread the argument or the path to the library file. And then I press enter, and now that's built. And then I can call this break from the dojo. So the pattern will be I do break call tapes lib, and then I can just use this arm like I would for another like a gate or whatever. And then as we can see, we can call that from the dojo. Let me resize these. So how about let's use these library functions in a generator. So something more like what you do in real code. So so here's a generator file. So let's save this as count word .hoon. So I save that in my gen folder. And as you can see, the first thing I do here is this fazless tapes, and that is going to be importing this library into my generator. And then the rest of the generator, it's just going to take a tape as input and a word as input, and it's going to count how many occurrences of that word are in that sentence. So, and here the code is super simple because we're just using this library function and this library function, and that's it. So all the complexity is kind of hidden in here. So with my generator now, so I can commit, and now I can just run my generator. So I ran my count word generator and it works. So I counted how many times the word the shows up in that sentence. It shows up twice. And if I do some random word, then it's going to give me 0 because that doesn't appear in there. So does that make sense to everybody? That's just like a super basic example of how we might use a library and use it from a generator or just like another file. Cool. Why is it? It's just it's just a random name that I chose. I could have just called it tapes, but I just like didn't want to overlap names to make you guys confused. You can call it whatever you want when you're building this. You can call it whatever you want. Yeah.
Will these files be in the GitHub repo with the next lesson plan?
No, but I could put them if you want. Yeah.
Yeah, I'd like to try running them on my machine, see what happens.
The count word generator isn't it?
Yeah.
Or just the libs tape.
Or-
Lib tape.
Yeah, this is a modification of some code that Neil has, so I just like modified it slightly. But yeah, we can update the lesson with this.
Okay.
Yeah.
If you don't mind too, if you put like a comment in there, the commands you use to run it too.
Oh, that's a good idea. Yeah.
Thank you.
When you have more complex Hoon expressions and you have all these gates that you've kind of just named yourself, does it not get confusing? Like, I guess if you're sharing Hoon between people and I don't know, you named it lib tapes, or tapes lib, but maybe somebody that's not very indicative to someone else.
Yeah, I think that's like a programming problem in general, right? Is how do you communicate things? Yeah, definitely an issue that requires some thought if you're working with other people.
I mean, that's kind of a problem that's endemic to library composition, period, right? Like actually knowing what's in the libraries.
So we got 2 minutes left, and I got one small topic left to cover. So I'll try to go quickly. So the last topic is going to be logging. So a super useful practice when you're coding, especially if you're trying to debug, is to log some output, some information to the terminal. And the basic tool we use for this is the sigpam rune. So let's go back to this generator we just wrote here, and let's add some stuff to it. So I had this line sigpam. Here is my word counting generator. And that's just going to print this to the terminal when I run this. Very simple, right? And I can add another line, sigpam. Now, see, there's an arrow here. That's what that's actually going to do is that's going to change the color of my input or my output to make it a little more distinctive. And here, kind of the cool thing we're doing is we're saying input string. So that's going to be the text. And then this is actually going to let us print the variable input in line with this. And we can also print the word. And finally, you can increase the number of arrows to change the color even more. So this is going to change the color again. And then this is going to make it a very angry color. So let's save this, commit base. And now let's try running our generator again. So now we got some nice output to the screen, right? So we got, here's my word counting generator right here. We printed the input string. We printed the input word in green, and we printed a warning in yellow and an error in red. So basically that's how you log stuff to the terminal. Are there any questions on that?
How many children does SIGPAM have to emphasize this point?
Oh yeah, so SIGPAM, it has two children. So one child is the thing you're printing, and then the next child is the rest of the code. So actually, if you just have like SIGPAM, like if I just do SIGPAM something, right? It's not going to do anything. And it's going to give me this left arrow because the code is not done. So I actually need to complete this with some Hoon code. So if I just give it a 1, then it'll print print my thing. So yeah, SIGPAM needs to have some code after it. Yeah. Any questions?
So I don't want to see code that ends in a SIGPAM. It won't work. You'll get a generator build fail.
Yeah, that's a common one. Mhm. All right, I think that's it for me. Yeah, I hope you guys enjoyed the lesson. And definitely feel free to come to office hours. So it'll be on Friday at 10 a.m. EST. I'm really sorry I missed Tuesday. If you showed up on Tuesday, my sincere apologies. But yeah, anything you need clarifications on, just show up or shoot me a DM or post in Hooniverse. So yeah.
I will get the lesson notes and everything posted to you tomorrow as soon as the recording from Zoom is ready to upload. So thanks, Jack. Thanks all.
All right. Do I just end the meeting now?
Yep, when you end, it will summarily dismiss us all. So
Okay.
good night.
Thank you.
Thanks.
I don't even know how to do that, to be honest. I don't know where the button is.
Lower right, end meeting.
Lower. But I'm in like the presenter mode where.
Oh, you have to exit that.
Okay. All right. See you, everyone.